It's in here. Hey everybody, welcome to the HTM Hackers Hangout. It's December 2nd, 2016. Every once in a while you're going to hear this really annoying beep coming from some smoke alarm or something in the office that needs to be replaced. The battery needs to be replaced, so I'll just apologize ahead of time. None of us engineers can figure out how to fix it, so. We're going to talk today about topology and boosting. And I think we might go straight to Yue, who's sitting on my right here. You may want, let's scoot over here. There we go. So one of the questions, I know David, you're on listening in, and one of the questions is, what's the deal with the new boosting? Why is there a new boosting code, and what's the difference between the old boosting way and the new boosting way? Should we try boosting now? If you're using a new pick, should you try boosting out again? That's a good question. So maybe you can explain why you did it and give a couple references, because there's the whole paper, that explains it.
Yeah, so the extended version of the description can be found in the Spatial Pooler paper, which is on bioRxiv now. And the whole idea of boosting is to encourage columns to be used efficiently. By that I mean every column in the spatial pooler should participate in representing the input. In the code, we implement it by applying a boost factor to each column. So in biology, we call that homeostasis.
Homeostatic regulation of neuronal activity.
Yes, that's the one.
Yeah.
So it's basically representing intrinsic excitability of the cell. The old boosting have a very discontinuous function.
I can show you that while you're talking about it. Keep talking out loud.
So it only
I don't want to.
You gotta do push to top.
Oh, push to top.
The sound dropped out for a second there.
That's okay. I don't want the sound. I wish I could just mute it. Is it distracting to leave it playing like this?
No.
Okay, go ahead, Yue. Just ignore me talking.
So this figure, this is showing the active duty cycle is basically how often a column becomes active in the past, maybe over the last 1,000 records.
Got it. Okay.
That's showing in the middle, and on the right is showing the
those are the boost factors.
The boost factor. That's
the labels are bad. Sorry.
Yeah, on the right is the boost factor, which is the excitability of a column. So a high boost factor means
we're not seeing that, guys.
You're not seeing this video at all?
No, not at all.
What's the point of having this module in?
I'm seeing the reflection of it on your forehead, maybe.
Well, I thought the whole point of this thing was so I could share YouTube videos. That's weird. So here, I'll just paste it into chat. Then there's a video here. What's that?
You're muted.
I am muted?
I don't think so.
I'm not muted.
No, it's that you're muted.
Can you hear me, David?
Sure. I'm fine.
Okay, sorry. So I just pasted the video into chat, and what it is it's a comparison of the way boosting worked before Yue's change and after. And the first part of the video shows it before, and you can see that it's not very effective. Like there's this phase where boosting starts, and it'll apply either no boost factor or one boost factor. There's no gradient at all. Yeah. And then when it's done, it's just done, and it drops everything.
That's right.
Yeah. But the new one that Yue did is much more dynamic.
That link is to the Hangouts, not to the video.
Yeah, that makes sense. Okay. How do I get back to? YouTube Flash AI was deprecated. And, okay. Okay, I'm getting the link now. Just give me a sec. Here we go. Here is the link in chat.
Share your desktop.
I could share my desktop. Yeah, that's better than nothing. Let's just do this. It's going to be a little bit slow to refresh, but it'll give.
So what I'm showing you here is.
Yeah. Okay. Let me mute. Okay. Got it. There we go. So as it's going along, you know, the big red block is the boost factors, and I think they're all at 1 right now.
This is before the change.
This is before the change, and so boosting kicks in, and it starts affecting sort of pseudo-random. Randomly, the green ones are the ones that are affected by the boost, and it's always max boost. So the green ones are boost factor is max boost, and the red ones are 1, and that's pretty much the way the old boosting worked. And it didn't seem to have the effect that we wanted. What's that, David?
I'm sorry. I'm having difficulties here.
Okay. So I'm skipping ahead to the new boosting visualization, and this is all. If this isn't coming across, there's a link to a video in the video description. So this is the new way. And the active duty cycle's in the middle. It's a red to green gradient. So the redder it is, the more active the columns are. The greener, the less active. And on the right-hand side where it says learning SP active columns, ignore that. These are the boost factors. And so there's a much more dynamic gradient of boost factors. It's not just max boost or nothing.
The change is actually a very simple change. I basically change what we call the boosting function from a discontinuous function to an exponential function. That's why you see the gradient and the continuous range of boost factors after the change.
Yeah, let me get back. I'll stop presenting here. Okay. It's off. Here we go. So, Dave, do you have any questions about that at this point? Did that explain why we did this?
I don't know what happened, but when I clicked on that link, I have a hidden screen now with your, and I'm listening to the video. Oh, there it is. Okay, now I can cut it off. So I didn't really get any of your explanation of what the colors meant as you were talking about them. So,
well,
I'm sorry.
The point is the old boosting applied. You know, you give it a max boost. Right, that's how you turn boosting on. If boosting is 1, that means the boost factors are always 1. That means it's effectively doing nothing to the column overlap scores. Yeah. And before, if you put max boost 10, those boost factors would either be for each column 1 or 10. And so there was no gradient. It was very all or nothing pretty much for how it would affect the columns overlap scores and whether it would be involved in as the winning columns or not. So as Yue was explaining, he applied this much more gradient way of calculating the boost factors. And it works a lot better. And if you look at the boosting HTM school video, you can see it working, really well. The whole point is to increase the efficiency of the spatial pooler so that more columns can represent more features of the input space. And it definitely does that a lot better than it did before.
So what is the tendency when you don't have an advanced boost like this? What is the characteristic behavior of the columns?
So typically there will be only a small fraction of the column in the spatial pooler that's being used to represent the input. So if you are not using all the resources you have, and the result, you can see that reflected in your model performance, like prediction accuracy. In fact, after the change of the boost factor, the examples like hot gym gets better performance.
Awesome.
Yeah.
and where's your tuxedo?
Don't make him regret that. That was a great picture.
So we have a PR in process. It's going through all this.
Yeah, so it's not quite merged. It's okay. I think the NUPIC core one is merged. NUPIC is not quite merged. We'll have to cut a release first. Yeah. So we'll probably cut a release today. I bet we'll get it merged today. So that all that new code will be in probably today. And I already, that's what I ran in the boosting episode of HTM School because I knew it was coming. And it made a lot more sense. So that's the boosting change. Let me see if there are some people watching, so let me see if anybody's chatting. If anyone has any questions, just jump into chat. I don't know if I turned the QA app on. I'll also check the YouTube page real quick because there's a way to add comments there. Yeah, nobody's there. Okay, good. Otherwise, I want to talk about topology. So I'll move on to that if there's no questions. Okay, so I've spent like this whole week talking to everybody in the office about topology because I was confused and I wanted to know the best way to message the community about why it exists and why we're not using it. Those are the two big questions. Why does it exist and why aren't we using it in NUPIC in most of our examples? So what I think I'll do is I have a whiteboard here. I'm going to sort of do a whiteboard thing, and I'm going to present you a visualization that I'm working on that I think explains topology pretty well, and then we can discuss it, and if anyone has questions, we can ask. I think this might be a good video to have to show to continue the topology discussions we've been having on the forums. And you guys can please correct me if I do anything or write anything that's wrong. So I'm going to try and do this sort of three-dimensional visualization where this would be like the spatial pooler cortical sheet, assuming there's a bunch of cells in this sheet, and we would have another sheet of this would be like the input space, the input axons that are providing feed-forward input to the spatial pooler. It doesn't matter the dimensions of this or the dimensions of this, but the key is if there is a column here in the spatial pooler, topology is implemented, I think. What's the matter?
Is there a way for us to mirror the screen?
No, they can see it fine.
Oh,
you can't.
So we're just
Yeah.
Yes, but you can just look there.
Yeah. So there's two ways in NUPIC and in current HTM theory that topology is applied. One is a calculation of the neighboring columns around this column, and that's involved in the boosting calculation and also in the inhibition calculation, right? And so getting the neighboring columns is a part of the topology because that makes associations between this column and columns around it. The way that these are calculated is a simple distance calculation. As you might know, when you define an SP, you can give it dimensions X, Y, Z, or just any number of dimensions. So assuming you've defined a two-dimensional input space like I've sort of drawn here, this would be some very simple geometric square around that column, and that's the column's neighborhood. So that's one way topology is applied. Another is this column or this input space sort of projects to that column, and it has a receptive field, again, which may be bigger or smaller than its neighborhood. It's not associated in the same way, but it has a receptive field down here of potential connections it could make to the input space. So how this receptive field is defined is also another aspect of the topology. So we've got the distal connections, that element of the topology, and these are the lateral connections, right?
Proximal.
Proximal, okay, proximal connections here. And the terms that were used for this is column neighborhoods, typically in the code. And that's what this box is, column neighborhood. And this would be, we either call it a potential pool or a receptive field. In the code, it's called potential pool. And every column has these two attributes. So one of the mistakes that I made when trying to understand topology was making too big of an association with the dimensionality that's defined for the input space and the spatial pooler with the topology. For example, this is like 2D. It could just be 1D, it could just be one huge array. And it's used for the calculation of the receptive field and the column neighborhoods for getting that distance. What columns are close to me? The dimensionality is used for making that calculation. So some of the interesting things here, we've got a column here that might project to a different input space than this one. You may have columns in the middle that have some, overlap with their different receptive fields. One of the things that I didn't quite understand is why don't we have this on all the time? It seems like it would be beneficial to have topology on all the time because, and I think one of the answers that I've come up with after talking to everybody is we don't necessarily need it at the scale of the structures that we're simulating at this point. So for example, we typically use 2048 columns in the spatial pooler. And our input space is typically, I don't know, 400 to 600 bits, sometimes larger, but not huge. And the interesting thing is, let's say this is our input bits, just all in an array. A lot of times we've got them separated up. You know, we've got one scalar value X here, another scalar value maybe inside this portion of the input space that's being encoded into bits, and then like date over here. So one thing that really makes sense is why we don't use topology is that if we did, we might have a bunch of columns that are mapped onto the date space that will never associate anything that happens over here, because that topology keeps that a local association. And then same way, you'll have a bunch of columns that you know, there's some overlap on the boundaries, but for the most part, a lot of these columns with topology applied, we'll never see the whole picture. And for 90% of the cases that we deal with NuPic and HTM, we want every column to have the whole picture, because then it can represent more like smaller portions of more of the data than like just one little piece of the data. I think it's better to distribute the representation across the columns than it is to have a bunch of localized columns that are fairly strongly associated with local spatial aspects of the encoding. People are nodding at me, so that's okay.
Question.
Yeah.
Is it okay now or later?
Now.
That was the question.
Was that the question?
No. That was my question about the question. At some point, can you guys include some discussion about why it is that you want bits to be to have a distributed membership within the potential pool? In other words, like what you said, why you want you know, the bits within the spatial pooler to have within their spatial pool a distributed you know, bits from the input field that are distributed, you know.
So you're saying, why is it desirable to have this property I was just explaining, to have a column not just represent one portion of the spatial input, but
like what does it do in terms of, you know, the spatial pooler's ability to distinguish inputs for one thing,
and help with noise, right? If you've got a column that's very focused on one part of the input, if there's noise in that input, it would activate more often than if its meaning was distributed throughout, because the noise would affect it more if it was focused on one area and it got noise in that area, versus less if it had more distribution throughout the space. That noise would affect it less because it wouldn't always be happening in all the spaces that it was connected to. Does that make sense?
Yes. Also, I guess if you had failure too, if you had bits die or somehow become disconnected or something, then having every bit in the spatial pool just have within its pool, you know, a wider distribution of bits would make it more resilient to, you know, cell death or whatever, or some kind of.
Each column, I say, may be less important to the overall picture.
Right.
It's better distributed amongst the columns.
I'm not sure I understand the question. Is the question, why is it better to have global?
Okay, so say those three input in the bottom array, you have X, Y, and say the last one was called, okay, X, Y, and date, whatever. And say the left bit in the spatial pooler up on top, the very left one, had a connection to all three sections.
Okay, yeah, so its potential pool will breach the entire input space. It's got some connections across the space.
So my question is, why is that
without
better?
Topology. This is without topology, global inhibition, no topology.
Oh, you want that if you want to have columns that encode combinations of values from different fields. So let's say you get, if you look at HotGym, if you get
7 here and 42 here on a Sunday.
On a Sunday, yeah.
That's what this is, right?
And maybe Y, if Y is energy level, maybe Y is really low on a Sunday during the day, but on weekdays, it's actually high during the day. You know, if you think about like a HotGym or energy example, you might want, I think you'd want columns that represent the combination of Sundays and during the day, you know, and low values, and maybe weekdays and high values. And you can only do that if the column is getting a common inputs from multiple fields.
That can be one of the main reasons to use a spatial pooler. Otherwise, you could just pass in sparse encodings if you didn't need this property.
Yeah.
And you want topology. Topology is helpful when you don't want that. Like usually in images, what's happening in one part of the image is not really related at a small scale to what's happening in another part of the image. Like whether you have a horizontal edge in the top left versus says nothing about whether you have a horizontal edge in the lower right. And so it would actually be bad to have global inhibition or global, no topology in that case. So it's really just about combinations that you want to encode.
I'm just thinking about spatial representations, there's, in the whole, this is something that several people told me when I talked to them about it, that if you're talking about an image, the entirety of the image, or the global aspect of the image, is not as important as understanding what's happening in this area, what objects are within this area, spatial recognition of here versus here versus here. But the way we encode data, we don't really do it like this. If you look at all the encodings that we've done, that I've shown on HotGym and HTM School, it's very important that you see not only the scalar value up in the very top left, but the date and the weekend encoding that's happening on the complete opposite spectrum of the encoding. That's important that every column has reference to all of those bits. So it's sort of an application-specific thing, but these are the types of applications that we've been building for HTM. Now, all of this being said, topology is still really important. Imagine in the future where we have these cortical structures that go on and on and on for who knows how long, when we're able to maintain that. There's no way to do global inhibition anymore, or you're going to have to do localized inhibition. So we're going to have to apply topology at some point. So it's a really important part of the theory. It's just something we're not forced to use right now for the applications that we're trying to build.
I have a comment. So I think it's important to make the distinction between, like, just in the terminology when you talk about the stuff. So there's one, you can talk about the topology of how the input bits are distributed. So in the visual sense, so this is like the two-dimensional grid kind of thing. And there's another aspect you can also ask. Now you can represent. Now you have your image which you represent by some state of this two-dimensional grid, and then these data points can itself have a intrinsic topology.
Yeah.
And so there are two questions here. So one is whether spatial pooling is somehow related to the topology of how the input bits are organized, and in the visual from the visual viewpoint, when you encode images or something like that, there seems to be an advantage of that. But then you can also ask, should the spatial pooler be look for this intrinsic structure? And so that's, I don't know, I will talk about it later, but that's the thing which I think is even more important, because so topology doesn't mean, so usually, so it's important more this neighborhood notion than this, whether it's two-dimensional, one-dimensional, three-dimensional. So that's not really, I would call that dimensionality or whatever, or how, that's just the, if you want to use a two-dimensional grid or an n-dimensional grid, but this notion of neighborhood, so there you can have, this is really sensitive to, so you can build very complex structures which Yeah, so you can mimic intrinsic topology. So that's
so what I think one of your points is you don't need the dimensionality involved with when you're defining the input space for topology to work.
Yeah, so I mean, in general, it will be very hard to if you have, say, you have a data stream. Even if you have say, I give you a data stream of like your collection of bits, so you have some ordering on it, and I give you images represented in that. So I just permutate an array, and then I ask you, can you tell me whether these inputs, whether the bits are actually organized in a grid? Like, can you tell me that by just looking at which bits are on for an image or not? If I give you 1 million images, so that's kind of these questions are involved here. So for visual, it seems very natural. But if I give you a bit array which represents just like black or white image, the positions, and if I permutate it, and then I give you like a bunch of it, can you tell me that it really comes from a 2-dimensional grid, for example? Yeah. So that, I mean, these are just related questions. So I'm just trying to. Yeah. So there's this extrinsic or intrinsic notion, and this like how the input bits are organized. So you have two kinds of topologies here, or two kinds of
Good example in the brain that I often use for this is like audio. Audio is just like a one-dimensional stream of inputs, but in the brain it's organized two-dimensionally with, like a kind of like a spectrogram. That's the easiest way to think about it, and you can almost process audio using images. So there you have a 1D input stream that it might make sense to organize in a 2D topology. That's just one example.
Yeah, and there's continuing discussion about that on the forum.
Okay.
Someone brought that up specifically.
Okay.
Sort of the topological fingerprint of audio streams.
And cortical I/O is another example. They take words where you don't think there's any topology, and they translate it into a 2D semantic space. Yeah. Where the topology is important.
So question.
Yes.
What makes the inhibition scheme local as opposed to global? So if I had two of those things, like in your continuation arrows, Matt, if you had another, say, sheet to the left of that, by virtue of you having two, you would then have local inhibition as opposed to global. So isn't there a change in the algorithm too for that? It's not just a simple beyond the consideration of neighborhood. I mean,
it's actually really simple. Just imagine that every column's neighborhood just got really big.
Right.
And, and every column's receptive field just got really big.
Right.
That's all global inhibition is just expanding every column's potential pool and neighborhood out to have to be part of the whole space.
So, but then you have that thing called the wrapping space, the wrapping too, right?
Yeah,
so
I think that's just
that neighborhood close to the end.
Honestly, I mean that's all that is. That just affects the neighborhood calculation and the potential pool calculation, so that it wraps to the side of it. But I don't think that's too relevant to the theory.
Okay. All right.
And I think you can do that with global or local. No, just global. That's a global.
Global doesn't matter. It's already looking at everything. So whether you wrap or not.
Right.
That's slow. Just slow. Right.
So that
it just means like if you've got a column on the side here and its neighborhood, goes over here, it's just gonna wrap it around to the side. That's it.
But doesn't that have some implications for cyclical data?
Absolutely.
Say okay.
That's why it's there.
Okay.
So, if you've got I don't know how to be used. If you've got it, I've been just playing with like animated GIFs, and some of the GIFs like repeat, and they'll run off one side and come up back on the other. That's a valid way to wrap it.
Right.
Valid reason to wrap it. Any other questions? We have a few people watching. Well, that is pretty much what I want to talk about today. And this is all, been really informative to me on figuring out how I'm going to present this. So hopefully this makes sense and the community can ask questions, and I'll try and answer them in the next video. So I'll post this on the forum, and thanks for watching and helping out. Thanks everybody in the office too for putting up with all my questions about topology this week. I guess that's it, guys. Thanks for watching HTM Hackers Hangout, and see you next month. Happy holidays.
Thanks, guys.